Hi everyone and welcome back to another video. And today in this video, I am going to show you how you can find whether a person is suffering from COVID-19 or not using their CT scan of their lungs and some machine learning. I'm going to build a model and then train that model on finding whether that person is suffering from COVID-19 or not. I'm using a dataset of called SARS-CoV-2 CT scan dataset. It's available online on Kaggle, but I will also put a link in the description where you can find it easily. And also, if you want to download the code which I'm writing, you can just check the link in the description. It's available online with explained everything in details, and also I have commented every part of it. So the first thing I'm going to do is import required libraries. The first one, numpy as MP, import pandas as PD, matplotlib.pyplot as PLT. This is for visualization, and also for visualization, we are going to use Seaborn as SNS. After that, for image processing, we are going to use CV2 and import OS for files management, and from PQDM import PQDM. This is just a progress bar library that shows a progress meter during processing. And then from sklearn matrices import confusion matrix. This is to compute the confusion matrix to evaluate the accuracy of classification. After that, from sklearn selection import test split. This is to split the data into training and testing sets, which we are going to use to train a model. We are going to divide the model into 20 and 80, 20% for testing and 80% for training. After that, we got from paras.utils, categorical, then from paras.models, import model, sequential. These are all the deep learning models from Keras, I think deep learning models from Keras. After that, I'm also going to import the Adam. So Keras or optimizers, import Adam. After that, from Keras or view processing, what image, import image data generator. After that, from Keras or callbacks, check that. This is the thing which we are going to use to save the weights of a model and reduce learning rate when the improvement steps stops. After that, from applications, Densenet-121. This is a pre-trained deep learning model, and forgot to add few more things from yes, dense, dropout, flatten, max pool 2D, batch normalization, average pooling 2D, global average. Let's run this, and we have got an error. Cannot import the name load models. So it's not models, it is model. Everything is working fine. Let's move on. Now we are going to import a data set. So import data set. Disease. We are creating two files. One will be labeled as COVID, and another one will be labeled as non-COVID. Data dir. This means data directory or data directory because Indian. Copy, paste. And after that, we are going to also assign a train directory, which is OS path for join data directory. Let's run this and nothing. So that means our data is also imported now. After that, we are going to do train data defects ID disease types. Let me check the spelling. It's all right. The file name. About append. Let me just focus right here for a minute second. This will need to be no. This is for both the directory. No. I'm going to explain this once I have written this. So this will give me a second format. SP file defects ID. And this is going to be SP. Not train is equal to PD dot data frame train and data column file disease ID disease. Okay. So now we can see everything. Disease ID 0, that means there is COVID, and if disease ID is 1, that means it's non-COVID. So what this thing does. This code snippet is used to create a list of image file path and corresponding disease label from the dataset of COVID-19 diagnosis image. The dataset is organized into folder where each folder corresponds to a specific disease types, like for COVID and for non-COVID. There are 1,252 files in COVID and 1,229 files in non-COVID. So now let's break down the code. So the first line, train underscore data. This is an empty list called train underscore data is created to store the information about each image file and its corresponding disease type. Now for defects, SP enumerates this for loop iterates through the disease type list, which contains the name of the disease folder in the dataset. The enumerate function is used to get both the index and the disease folder name for each iteration. After that, coming to this nested for loop iterates through each file in the current disease folder. os.list_dir list all the files in the folder specified by os path join, where train directory train underscore dir is a root directory containing all the disease folder, and sp is the current disease folder name. After that, this line, for each file that is an image in the current disease folder, a list containing the relative file path, which is this one. The disease index defect and the disease is appended in the SP or the train underscore data, which is appended into this. So this just iterates through all of our files and then distinguish it between whether it is a COVID file, sorry, a COVID image, or whether it is a non-COVID image. So this will just append the list. This is an empty array which we are going to use to train and test afterwards. After that, coming to this line number 6. Once all the files and their corresponding disease or information has been added to the train underscore data list, a pandas data frame named train is created. The data frame has 3 columns: files for the relative path files, disease ID for disease index, and disease type for disease name. As you can see, disease type is COVID and file name is this, and disease ID is 0, 0 for COVID and 1 for non-COVID. Train.head, this line displays the first 5 rows of train data frame, which is this one, which provide us a glimpse of data. This is helpful to ensure that the data frame was created correctly and that the data is in expected format. In summary, this code snippet creates a Panda data frame containing the file paths and corresponding disease label for dataset of COVID-19 diagnosis image organized into folder disease type. After that, I'm going to let's randomize the order of training set. We're going to succeed to 42 train.sample. That is one random state is seed train.index is np.orange. Then this is going to reset indices, and then let's check. All right, there is another. It's not double R, it's a single A range. All right. So this code snippet is responsible for shuffling the train data frame created in the previous snippet. And then this one, we created a train data frame. And also to ensure that the order of the data is randomized. Randomizing the order of the data is important in machine learning to avoid any potential bias due to the initial ordering of the data set. Here, now let's break down the code. So line number 2, seed is equal to 42. This line sets a constant value called seed to 42. The purpose of this seed value is to ensure that the randomized process is reproducible. By using the same seed values, you can obtain the same random order of the dataset every time you run the code. After that, coming to train line number 3, this one, the sample function is called on the train data frame to shuffle its rows. The frag parameter is set to 1, which means that all the rows in the data frame should be included in the shuffled output. The random underscore state parameter is set to the seed value to ensure reproducibility. After that, this line resets the index of the train data frame after shuffling. The np.arrange function creates a new numpy array with consecutive integers from 0 to length train -1, which is the total number of rows in the data frame. This new array is assigned to index property of the data frame, effectively resetting the indices to a new sequence of consecutive integers. In summary, this code snippet shuffles the train data frame containing the file path and corresponding disease labels for a dataset of COVID-19 diagnosis image, ensuring that the order of the data is randomized to avoid bias. It also resets the data frame indices and displays the first 5 rows of the shuffled data. And to display the first 5 rows, we are going to use train underscore head. Now let's plot our data, a histogram to see how many files are there in the COVID folder and non-COVID folder. So it would be pretty much identical because there are about 1,200 files in both the folders. So the chart should look exactly the same. Let's just plot it. So we are going to use matplotlib. We imported it as PLT. So we are going to call the matplotlib library, and figure size. Here we define the figure size 12 by 12, and we want a histogram and the train disease ID, and the title is going to be frequency histogram of species, and plt.show presents the chart to us. So look, it's almost identical, but one is bigger. One is bigger because COVID has more files than non-COVID, so the COVID file is bigger. Let's now display the images of COVID. Once I will write down the code and then I will explain to you in much detail, and I will also go through line by line. So let's start there. Defects. Subplots. Defect files, and this is going to be just n. Now let's display the image. So plot, let's call the function defects and pass it COVID, and that is going to 5. Let's run this. So there's an error. A is not defined. Where is A? Files. All right. So now let me explain you what this code does. So this code snippet defines a function called plot defects that displays a grid of images for a specific disease type from the trained data frame. The purpose of this function is to help you visualize and inspect the images in the dataset. Now let's break down the code. So the first line, which is the second line in our case, the plot defects function is defined with 3 parameters: defect underscore type, which represent a disease type, with example COVID, which we pass through this, and rows, the number of rows in the image grid, and number of scores, the number of columns in the image grid. So we wanted 5 image, and it's 5. So it's a 5 by 5 frame, and it's just COVID. So we can also pass it non-COVID, and it is going to print the data from our non-COVID folder. So right now we just leave it to COVID. After that, the third line, the plt.subplot function is called here to create a grid of subplots with the specified rows and columns values. The fixed size parameter is set to 12 by 12 to specify the width and the height of the figure in inches. The function returns a figure object and an array of axes ax. So this will return us 2 things. One is fig and ax, which is axis. After that, the line 4. This line filters the file column of the trained data frame to select only the rows where the disease type column equals to the specified defect types. The dot value attribute is used to get the underlying numpy array of filtered path. N is equal to 0. This is a counter variable. N is initialized to 0. This variable is used to iterate through the selected image file path. The nested for loops iterate through the rows and columns of the grid of the subplot. For I and range in rows, this iterates through the rows of the grid. For j in columns, this iterates through the column of the grid. Inside the nested loop, this line, the os.path join function is called to concatenate the root directory data dir and the current image file path defects file, which is an n, sorry, which will help us to get the full path of the image. This line removes the x-axis ticks from the current subplot, and this line removes the y-axis tick from the current subplot. The IMShow CV2 is then called on the current axis, which is ax, I, and j, to display the image in the subplot n plus 1. The counter variable n plus 1 is incremented by 1 to move to the new file. So we initialize it at 0. We iterate through the rows, then the columns, then we get the image file. We remove the text from the x-axis, we remove the text from the y-axis. We assign the new path as the current path as the image which we have just read, and then n is incremented by +1, and then it goes back again, and it then keeps everything doing again and again, so that we can see all of the images in the file. So in summary, this code snippet defines a function called subplot defect that displays an image grid of image for a specific type of diseases from the trained data frame. The function is called to display 5 by 5. And as I showed you, we can also see non-COVID index. So it's quite, let me just copy it and paste it. So we can see both at the same time, non-COVID and COVID. Yeah. Now let's read the image and resize it. So image read and resize function. Images. All right. So this code snippets defines two utility functions, which is read image and the resize image, that are used for reading and resizing images from the dataset respectively. Now let's break down the code. So the first line, image size is equal to 64. This line sets a constant value called image size to 64. This value will be used later to resize images to a fixed size, which is 64 by 64 pixels for model training. After that, the read image function is defined with a single parameter, that is file path, which is the relative path of an image file, and then return cv2.imread. The cv2.imread function is called to read the image file specified by the file path parameter. Then the os.path.join function is used to concatenate the root directory data_dir and the relative file path to form the full path of the image. The cv2.imread function returns the loaded image as a numpy array. Then after that, we got a function called resize image. The resize image function is defined with two parameters: image, which is the input image as a numpy array, and image size, which is the target size for the resized image, both width and height as they are assumed to be equal in this case. After that, the cv2.resize function is called to resize the image to the specified image size. Then the .copy method is used to create a copy of the input image before resizing and to avoid modifying the original image. The interpolation of parameter is set to cv2.enter_area, which is a recommended interpolation method for downsampling images. So in summary, this does do two things. One is to read and then to resize the image. After that, let's start with training images. So x_train mp.zeros, train.shape 0, image size, image size I will set it to 3. It's fungus, and this should go till 2400 hits because that's how many images we got. We got around 2400, and let's see. Yep, 2481 on point, boss, on point. We got 2481 images, which is 64 by 64 pixels, and they are divided into 3 files: one for COVID, non-COVID, and for training. So what does this code snippet does? This code snippet creates an array xtrain that stores the resized and normalized images from the trained data frame for further processing and model training. Here is the background of the code. So the second line, this is a numpy array called xtrain of zeros is created with a shape, which are number of training samples, image size, and 3. The first dimensions correspond to the number of images in the training set, and the other dimension represents the height, width, and the number of color channels, which is 3 for a red, green, and blue RGB of the resized image. After that, a loop is created to iterate through the file path in the file column of the train data frame. The TQDM function wraps the enumerated functions to display a progress bar while looping through the file path. Then the read underscore image function is called with the current file path to read the image. If image is not none, which is this one, the resize, sorry, hold on. And if statement checks if the image is not none, that means that we have successfully read the image. After that, in line 6, the resize underscore image function is called with the loaded image and the target size, which is 64 by 64. The resized image is then assigned to the corresponding position in the X-train array. After that, we got in line 8. The pixel value in the X-train array are normalized by dividing them by 255. This scale the pixel value to the range of 0 and 1, which can help improve the performance of the neural network during training. The normalized data is stored in a new array named X train with capital T. After that, we just use a print statement. The shape of the X train array is printed to provide information about the dimensions and the process data sets. Now we are going to convert labels to categorical. So y underscore train disease ID dot values categorical y underscore train num is not divided. Oh, it is num underscore classes. Please work. So yeah. So this code snippet creates a one hot encoded array called y underscore train for disease label in the train data frame. One hot encoding is used to convert categorical integers label into a binary vector that can be used as a target for model training. Now let's break down the code. The first line, this line extracts the disease ID column from the train data frame as a numpy array and assigns it to the variable y train. The disease ID column contains integer label representing the different types of disease, i.e. 0 for COVID and 1 for non-COVID. Then the third line in this box, the to underscore categorical function from the Keras library is called to convert the integer label in the y underscore train into one hot encoded vectors. The num underscore classes parameter is set to 2 as there are two disease types, mainly COVID and non-COVID. The resulting one hot encoded array is assigned back to the y train variable. For example, if the original y train variable, let's say, for example, if the original y train array contains a label with 0, 1, 0, and 1, then the one hot encoded y train array will look like this. It will look like 0, 1, sorry, 1, 0, and 0, 1. You get the point. So this is what this, in summary, this code snippet splits one hot encoded array for y underscore train for disease label and in the train data frame. The one hot encoded array can be used as a target for model training. After that, we are going to train test splitting. So batch size 64, split train and validation sets. All right. So let's take a break here and I will be back very soon. So this code snippet splits the preprocessed dataset, which is X-train and Y-train, into training and validation sets using the train test split function from the sklearn library. Validation sets are used to evaluate the model performance during training and help prevent overfitting. Now let's break down the code. So the second line of the code is a constant value called batch underscore size is set to 64. This value represents the number of samples that will be processed through the model at each training iteration. It is also basically called batch size. After that, the fifth line, the trains test split function is called with the following parameters. X-train, this is the array containing the resized and normalized images. Y-train, the one hot encoded array of disease label. Test size, which is 0.2. This parameter specifies that 20% of the data will be used as a validation set, which is also a test set. Random set is equal to seed. The random seed is set to ensure reproducibility of the split. The train test split function returns 4 arrays, X-train, Y-val, X-train and Y-train for the training set and X-val and Y-val for the validation test. In summary, this code snippet splits the preprocessed dataset into training and validation sets using the train test split function. It also sets a constant value batch size to 64, which will be used during the model training. So now let's do one more thing. Let's do 64. So it's finally working now back again. There was some error with disease type. As I stopped the notebook, something changed in the data set. I changed it and I didn't update it in the notebook. That's why there was that error. Now that it has fixed, we can move on. So this code snippet displays the first three images from the X underscore train array along with their corresponding disease type label. Here, now let's break down the code. So the first line, let me view double line number. So in line one, it is a 1 by 3 grid of subplot is created using plt.subplot function with a figure size of 15 by 15 inches. The function returns the figure object fig and an array of axis object ax. In line two, a loop is created to iterate over the indices of the first three images in the x underscore train array. Inside the loop, the third line, the axis is turned off for the current subplot using the set underscore axis underscore off method. This hides the axis label and ticks, providing a cleaner view of the image. After that, we got the imShow method is called on the current axis object to display the ith image from the X train array. After that, in line 5, the set underscore title method is called on the current axis object to set the title of the subplot. The title is the disease type corresponding to the ith label in the white train array. The np.argmax function is used to find the index of the maximum value in the one hot encoded label, which correspond to the original integer label. The disease type list is then used to map the integer label back to the disease type string. Now let's moving on. Let's make code blocks. And this epochs size equal to 64. So this code snippet defines three constant value that will be used during model training. The first line epochs, the epoch constant is set to 50, representing the number of times the entire training dataset will be passed through the model during training. Each epoch consists of multiple iteration, which are batches covering the entire dataset. Size equal to 64. The size constant is set to 64, which is the same as the previously defined image underscore size in this. Where is it? Right here, image resize function. This value represents the width and the height of the resized image in the dataset. N underscore ch, the N underscore ch constant is set to 3, representing the number of color channel in the image. 3 is for RGB. These constant value will be used as parameters in the Densenet model or during the training process. So now let's call on the Densenet model, sorry, Densenet-121 model, and let's start coding. The def build Densenet N underscore ch x is equal to 2D, which is 3. So it should be 3, 3 by 3. Parity is going to be same. And input x is equal to instant x validation. This is x. So it is 0.5. This is also going to be x. Don't worry about this. I will explain when I write this code. I don't speak during writing the code because it prevents some errors to happen. I can fully concentrate on writing the code, and that's why I can make sure that I don't get any errors. But I will explain to you guys once I have completed this. Catch normalization. Input and output. Minimize Adam. LR is 0.002. Data underscore is 0.9. Epsilon is equal to 0.1. Now let me explain to you guys in quite a detail. So this code snippet defines a function called build underscore Densenet that builds a modified Densenet one-to-one model for the COVID-19 diagnosis task. The Densenet one-to-one is a popular convolutional neural network or CNN architecture known for its efficiency and performance in image classification tasks. Now let's break down the code. So the third, let me just make this first line. So the first line, the function build underscore Densenet is defined with no input parameters. In the second line, the pre-trained Densenet one-to-one model is loaded with a top layer, which is a classification layer using the Keras library. The model is initialized with weights pre-trained on ImageNet dataset. So this pre-trained architecture is also pre-trained on the ImageNet dataset. After that, in line 4, an input tensor is created with the shape, size, and ends underscore ch, representing the height, width, and the number of color channels of the image. After that, in line 5, which is this one, in line 5, a 2D convolutional layer with 3 filters of size 3 by 3 and same padding is applied to the input tensor. The output tensor x will have the same height and width as the input tensor. After that, now talking about lines from 6 to 12. X is equal to Densenet x. The Densenet one-to-one model is applied to the output tensor from the previous layer. X is equal to, in line 7, a global average pooling layer is applied to the output tensor from the Densenet one-to-one model. This operation reduces the spatial dimension to 1 while keeping the number of features maps unchanged. A series of layers are added for the further processing. In line 8, batch normalization is applied to normalize the input tensor. And in line 9, a dropout layer with a rate of 0.5 is added to help prevent overfitting. In line 10, a dense layer with 256 unit and a ReLU activation function is added. In line 11, another batch normalization layer is added. And last but not the least, in line 12, another dropout layer with the rate of 0.5 is added. Now talking about in line 15, a dense output layer with 2 units for one for each class, which is COVID and non-COVID, and a softmax activation function is added. The softmax activation ensures that the output values are probabilities that sum to 1. In line 18, a Keras model is created by specifying the input and output tensors. In line 19, an Adam optimizer is configured with the learning rate of 0.2, beta 1 of 0.9, beta 2 of 0.9, and ellipson of 0.1, and decay of 0.0. In line 20, the model is compiled with the categorical cross entropy loss function, the configured Adam optimizer, and the accuracy metric for evolution. After, in the second last line, which is line 21, the model architecture summary is printed, and at the end, we return the model. That is, the build and compile model is returned. So now let's run this, and there should be no errors. Exactly, I said there are no errors. So now let's add a markdown and label it data augmentation and fitting model. Code. And this is to generate batches of images, data with data augmentation. So data gen is image, data generator, rotation range is going to be 360. So degree range of random rotations. After that, we got width, and this was shift range is 0.2. And this is range for random horizontal shifts. After that, we got height, shift, range is 0.2, and range for random vertical shifts. After that, we got zoom dot range, and this is the range for random zoom horizontal flip is true. This is randomly flip inputs horizontally vertical flip is true, and this is to randomly flip inputs vertically. After that, we got data gen, the fit, X-ray. It's the model on patches with the real time data augmentation. Verbal is true. Callback says vanilla. Check one. Validation data is X underscore Y underscore. Well, let's run this and hope. I will explain to you guys once. Let me just run this so I don't get any error. All right, we got one error. And what is it? Keyword argument not understood. Activations. We have just got epochs 1 of 50. And this should be 50 out of 50. So let's wait, and I will see you guys once it is trained on all 50 epochs. After that, it should only take few seconds, but I don't know why this is taking so long right now. Because it should just really go, 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 go. But not now. All right, it's happening, but it's happening very slowly. So let me explain the code till then. So this code snippet trains the Densenet model using the modified Densenet-121 model built by the built Densenet function. It also set up learning rate reduction, model checkpointing, and data augmentation. Now let's break down the code. The first line, the Densenet model is built using the previously defined built Densenet function. An annealer in line 2 is a reduce LRO on plateau callback is created to reduce the learning rate when the validation accuracy plateaus. The learning rate will be reduced by the factor of 0.5. If there is no improvement of validation accuracy for 5 epochs, the learning rate is set to 1E and 1E-3. After that, in line 3, a model checkpoint callback is created to save the best model based on the validation loss during the training. The best model will be saved in a file named model.h5 as we have defined it here. And after that, data gen is an image data generator object is created for real-time data augmentation. It applies random transformation to the training images such as rotations, shifts, zoom, and flips to increase the diversity of the training data and help prevent overfitting. After that, in line 12, the fit method computes any required internal data statistic for the specified data augmentation. From line 14 to line 19, we got this is the model is trained using the fit underscore generator method. It takes the following parameters: x underscore train, y train, batch size is equal to batch size. A data generator that will yield batches of augmented data from x train and y train with the specified batch size. After that, in line 15, this is the number of steps to complete one epoch, and epoch is equal to epochs. This is the number of epochs to train the model for. Verbose store will display training progress with verbosity level 2, 1 log line per epoch. In line 18, the list of callbacks to apply during the training, and at the last, we got the validation data to evaluate the model at the end of each epoch. After running this entire code snippet, the Densenet model will be trained using real-time data augmentation, and the specified callbacks. The training history will be stored in the hist variable, which is this one. And now let's see with a epoch 11, and we are at epoch 28. Let's wait for some more time. Then it goes to. So as you can see, the validation score is also increasing as we go down the line. It also decreased at some point, which was 0.782, accuracy 8.7, 8.9. Now it stands at 8. The accuracy validation loss also increased, and accuracy also. I need this number to be as close to as to 1, and this number also to as close as 0. And this is as far as away it can be from dot 1, which is 0.0. Let's see how the model performs. We will also make a confusion matrix. And then after this, we are going to make a final loss and accuracy to check how much we have lost and how much, what was the accuracy. So let me drink some water. I have been talking for a very long time. Can you see the CPU thing? It's in the red. I don't always see Kaggle CPU in red, but as we are working with a very, very, very big file, the output is around 19.5 GB, which is a huge. But let's see, I hope the output remains quite nice. We get a good confusion matrix and good chart. And at the end, it should be able to predict whether a person is suffering from COVID or not. Well, I lost it down. Holy shit, it's 4028. Accuracy sign, we need more variation. It's done, I think. Now it should be print. Now it's done. We have already trained 50 out of 50. Now let's add final loss and accuracy. So final underscore loss and final underscore accuracy is modulo evaluate x underscore val, y underscore val. So the final loss is as far as we can expect, and the accuracy is as close to 1 as we can expect. In real world, this is quite good, but in the ideal world, this should be 1 and this should be 0, but we are going to never reach to that point. So what does this code snippet does? This code snippet evaluates the performance of trained Densenet model on the validation dataset. The evaluation metrics are the categorical cross entropy loss and accuracy. In line 1, the evaluate method is called on the trained model to compute the loss and the accuracy on the validation dataset, which is xval and yval. And line 2, this is the computed final loss and final accuracy are printed. After running this code snippet, we can see the model's performance on the validation dataset in terms of loss and accuracy. This gave us an idea that our model worked really well, and it can also work on really unseen data. So now let's print a confusion matrix. So y underscore red is model dot predict x underscore value, y underscore red is simply dot arg max, y underscore red axis this will be 1, y underscore true axis will be 1, cm is equal to confusion matrix, y is true, y is red. Figure size will be 12 by 12, and this is going to be heat map. Cm cmap is plt dot cm dot greens. My notation is going to be true. So it's going to be true. X tick labels. All right, we got an error. And font size spelling is wrong. So it should be font size. COVID-20. So actually, our model performed far too well. So this code snippet generates a confusion matrix for the Densenet model prediction on the validation dataset and visualizes it using a heat map. The confusion matrix help us to understand the performance of the classification model by showing how many instances of each classes are correctly and incorrectly predicted. So correctly, it was non-COVID, it was 22 point E. So a lot of our models were correctly predicted, and that's a really good thing. But not with the non-COVID. Non-COVID, we had some problem. But now let's see an accuracy and loss curve. So I won't explain this line by line as this is pretty basic and yeah, it's pretty self-explanatory. So if you want me guys to explain it too properly, so just let me know in the comment box and I will explain it in the next video. So you will know. So explaining this is going to be the info without legend. Train test velocity upper left dot show and the loss plot is start history. We are going to go with loss function plt dot plot and his dot history. This is going to be the validation loss. So val loss plt dot title. This is going to be model loss, and then the y label is loss, x label is epoch, and train test LOC is upper left, and then we are going to do the plt dot show. So this is pretty standard chart. I can see the accuracy at the starting, the accuracy is always zero because the model doesn't know shit. And as the number of epochs increases, the accuracy also increases because the model starts learning what it really needs to do. And model's loss will also decrease as the number of epochs increases because the model now know what not to do and what to do. So this code snippet creates two plots to visualize the training history of the Densenet model, the model accuracy and the loss over time, which is epochs. These plots help us understand how the model evolves during the training process and can help identify potential issues like overfitting or underfitting. The rest of this is pretty self-explanatory. It's really basics of matplotlib, and that's it. Now the main part that why I have written so much code and gave it about 2 hours of my life. You guys will only see about 1 hour or so, but I gave it a lot more than 2 hours in searching for error and going through Kera documentation. But now let's predict from image, from SK image, import IO, from Keras dot pre-processing, import image. So we are going to give it what should we give it, a COVID image or non-COVID image? What do you guys think? So image dot load image. I am going to give it a COVID image. Right. COVID. Oh, oh, oh. Show 122 more. Oh, oh, oh. Oh, oh, oh. I am going to give it this one. 171. Paste. The PNG. Good. Grayscale is equal to false. I don't need any grayscale, just a normal image. Target size is equal to as with a image size 64 by 64. Good, 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 good. Show underscore image. This image dot load underscore img. The same image. Grayscale is false. Target size is equal to 64 by 64. Disease class is going to be COVID-19 and non-COVID-19. X is equal to image dot img. So array img x is equal to mp dot expand there. And x from axis is equal to 0. x125 custom model dot predict print custom 0 print prediction disease class dot run this. Bro, seriously seriously let's run this. The show image is not defined. Wow. Wow. IMG. Yeah. It's actually wrong. It's actually wrong. I gave it a COVID image, not a nonetheless. Let's just give it a non-COVID, right? Let's try this. Paste. Paste. Now let's run this. This time it worked. It said that it's not COVID. So why the fuck it's not running in this with COVID? Paste. Paste. Run. Yes. Come on, Chopper. Let me provide it with. It's saying non-COVID because it's. Now I understand why. I am going to fix this in the next video. So it worked right the second time. Not why not this time? Disease class is all right. We trained the model properly. It gave us no error. COVID-19 is. We gave it a COVID image now. It's image.load img. It's right. Grayscale is false. np.access is all right. Yes. Yes. Now it should work all right. Let me provide it with another COVID image. So copy file path. And it should predict that this person has COVID. Paste. Run. Yeah. Which is sus. And now let's provide it with a non-COVID file and paste it. It should predict that it is not COVID. So run this. Which I'm sus. And all right, guys. If you want to download the source code, check the link in the description. And also, if you want a written explanation, then also you will find that in the description. And I have wrote an article explaining each piece of code line by line, what it does, what the output means. So please do check the link in the description. Until then, bye-bye.